Hello everyone, my name is Samyam Raj Bhandari. I work at the Microsoft DeepSpeed team as a research architect, and today me and my colleague Tunji are going to present our paper ZeRO-Infinity, Breaking the GPU Memory Wall for Extreme Scale Deep Learning. In the last 2 years, model sizes have increased by roughly 240 times, while the amount of GPU memory has increased by just about 2 times. It is no longer possible to fit large models on a single GPU device, and DL training systems have evolved to combine multiple forms of parallelism, such as tensor slicing, pipeline parallelism, and ZeRO to leverage the aggregate GPU memory in a cluster, supporting these large models. Given the current large model training landscape, three questions arises. First, how do we sustain the growth in model size when the aggregate device memory is no longer sufficient to fit large model for training? Two, once large models are trained, how do we make them more accessible for fine-tuning? And three, existing technologies like 3D parallelism that uses tensor slicing and pipeline parallelism requires major code refactoring, which is error-prone and painful. Is there a way to simplify the pipeline for data scientists for large model training? In the next slides, I will talk about how we can address these challenges with ZeRO-Infinity. Let us start at the GPU memory wall. If we look at modern GPU clusters like the NVIDIA DGX2 SuperPod, they actually have heterogeneous memory where the aggregate GPU memory accounts for less than 2% of the total memory in the system. From a memory perspective, a single DGX2 node can support training a 20 billion parameter model with GPU-only memory, but if we can leverage the available CPU and NVMe memory, it could support training a trillion parameter model. A model like GPT-3, which has about 200 billion parameters, can be fine-tuned on a single DGX2 node. So how can we leverage non-GPU memory? Can we simply just extend existing parallel technologies to leverage CPU and NVMe memory? Let us first take a look at what are our candidates. First, data parallelism replicates data across devices and it thus causes a memory explosion due to redundancy. This problem will exist even if we offload data to CPU or NVMe memory. Tensor slicing cannot scale beyond a single node, even when the data is in GPU memory, and therefore it cannot work when data is in CPU or NVMe memory either. Pipeline parallelism, on the other hand, can scale across nodes and offers great efficiency, but it also requires significant model code refactoring that defeats the goal to simplify large model training. But what about the zero redundancy optimizer? It can not only scale efficiently across nodes to support trillions of parameters, but also does not require any model code refactoring. So ZeRO seems like a promising candidate. Let's do a quick recap of how ZeRO works. So ZeRO is a memory-efficient form of data parallelism. In data parallel training, each GPU stores a replica of all the model states. However, in ZeRO, each GPU only stores a mutually exclusive subset of parameters, entirely removing the redundancy. During training, when a parameter is needed, it is broadcasted from the owner GPU of that parameter to all the other GPUs over the GPU interconnect like the InfiniBand. So how can we extend ZeRO to use non-GPU memory? Can we simply offload the model states to CPU memory or NVMe memory and move them to GPU only when they are needed? In theory, this would take us beyond the GPU memory wall, but in practice, for this to be useful, it is also necessary for the system to achieve good efficiency or throughput. To understand the impact of this offloading strategy on throughput, we perform an analysis that measures the impact of bandwidth between GPU and NVMe or CPU memory on efficiency. For our analysis, we define a simple efficiency metric as a ratio between compute time and the compute and communication time. The compute time is estimated as a function of the total computation during each iteration of the training and the peak achievable throughput achievable in the absence of communication. The communication time is estimated as a function of total data movement and the slowest data movement bandwidth in the critical path. Now we can rewrite the total data movement as a function of total computation and arithmetic intensity with respect to different data used during the training, and obtain efficiency as a function of data type, communication bandwidth, achievable peak throughput, and arithmetic intensity for a given set of model and training parameters. In summary, what this means is that with our efficiency formulation, we can plot efficiency as a function of bandwidth for different data used in the training, such as parameter, gradients, optimizer states, and activations for different batch sizes. These plots can tell us for a given data type, such as the parameter or gradients, or the optimizer state, and a given batch size, how much bandwidth is necessary for ZeRO with CPU or NVMe offload to remain efficient. For example, for training with ZeRO to be efficient on a DGX2 system where each GPU can achieve about 70 teraflops in real performance without communication, we need about 60 gigabytes of offload communication bandwidth to read and write parameters and gradients. We need about 1.5 terabytes of bandwidth for optimizer states and 4 gigabytes for activation if we use a batch size of 2,000 tokens per GPU. Now, given these requirements, let's consider training a massive model on 1,000 GPUs or 64 nodes of DGX2 with ZeRO, where parameter gradients, optimizer states, and activations are all offloaded to CPU or NVMe memory. The NVMe bandwidth on a DGX2 system is about 28 gigabytes per second, while the CPU memory bandwidth is a couple of hundred of gigabytes per second. For parameters and gradients, since each parameter is owned by a unique GPU in ZeRO, the bandwidth from NVMe to CPU is actually limited by a single PCIe link bandwidth between that GPU and the NVMe memory, which is only about 12 gigabytes per second. This severely limits the efficiency of ZeRO compared to running it directly from GPU memory. Optimizer states, on the other hand, are updated in parallel across all nodes in ZeRO. Therefore, the required data movement can occur in parallel across all nodes, achieving an aggregate NVMe bandwidth of 1.7 terabytes per second across 64 nodes. This is more than sufficient to achieve good efficiency. Furthermore, while activation memory bandwidth from NVMe is insufficient to be efficient, the bandwidth from CPU memory is sufficient to achieve good efficiency. So in summary, our analysis shows that ZeRO with CPU or NVMe offload can enable offloading of optimizer states to NVMe and activation memory to CPU, but requires parameters and gradients to stay in GPU memory. While this is very encouraging, leaving parameters and gradients in GPU memory still creates GPU memory bottleneck. So can we do better and offload everything to completely transcend the GPU memory wall while still remaining efficient? This was one of the main motivations behind the design of ZeRO-Infinity. In ZeRO-Infinity, we partition each individual parameter across all data parallel GPUs before offloading it to NVMe. When a parameter is needed during training, each of its partition is moved first to the owner GPU using multiple PCIe links in parallel. Then, to reconstruct the full parameter on each GPU, it uses an all-gather operation instead of a broadcast. My colleague Tunji will show this in action shortly. Note that this remapping of data allows the NVMe to GPU bandwidth to increase linearly with the number of data parallel GPUs. On a single DGX2 node, we can achieve near peak NVMe bandwidth of about 28 gigabytes per second, and on a 64 node cluster, a massive 1.8 terabytes per second bandwidth, far beyond what is needed to offload the parameters and gradients. The impact of this linear increase in bandwidth is demonstrated with the figure in the bottom, showing weak scaling of ZeRO-Infinity and ZeRO offload for the backward pass. Note that both of them have similar performances on a single GPU, but ZeRO-Infinity gets over 2x faster with larger number of nodes due to increased aggregate NVMe bandwidth. In fact, at scale, ZeRO-Infinity is no longer bottlenecked by NVMe or CPU bandwidth at all, but actually rather by the GPU to GPU bandwidth of the all-gather operation. Next, my colleague Tunji will show ZeRO-Infinity in action and provide a deeper dive into optimizations and performance of ZeRO-Infinity.
Let's now see an animation of ZeRO-Infinity in action during the forward, backward, and optimizer stages of training. Each rank fetches a partition of model layer from NVMe storage, performs an all-gather in the InfiniBand network to assemble a full layer. It computes this full layer to generate activations that will be used by subsequent layers and during the backward pass. During the backward pass, the layer partitions are fetched in a similar fashion, assembled in InfiniBand network for generating gradients. These gradients are reduced across the ranks and then partitioned to be written out into NVMe storage. During the optimizer step, each parameter and gradient will be fetched into CPU memory to perform the optimizer step, which updates the model parameters. The updated model parameters are written out to NVMe storage, where they'll be used to process the next training input. ZeRO-Infinity employs powerful optimizations to achieve good training efficiency. One such optimization is the overlap-centric design, which ensures that data communication across NVMe, CPU, and GPU memories overlap with GPU computation to effectively hide communication latencies. This means that layers are prefetched ahead of use, and that prefetching overlaps computation of earlier layers. So for example, the figure here is showing that the computation of layer I in the GPU is overlapped with the prefetching of layer I plus 1 from CPU memory into GPU, and also with the prefetching of layer I plus 2 from NVMe into the CPU. The overlap-centric design is implemented using the Infinity offload engine of ZeRO-Infinity. This engine manages the pinned CPU memory buffers that are used for communication with both the GPU and the NVMe, and it also utilizes the deep NVMe module for fast data transfers to NVMe. The offload engine can be utilized as an independent library for workloads that require offloading to CPU or NVMe memories. ZeRO-Infinity enables easy integration into models by automating data movements and model partitioning. ZeRO-Infinity provides automatic data movement by registering model parameters so that it can intercept accesses to them and thereby materialize these parameters before they are used, and also release the memory used by the parameters right after use. ZeRO-Infinity also enables the initialization of models that are much larger than the available CPU memory or GPU memory. It does this by automatically partitioning the model parameters during model construction. These features are available by simply wrapping the model construction logic with the ZeRO-Infinity Context Manager. We will now review some evaluation results for ZeRO-Infinity. First, ZeRO-Infinity enables massive model scaling, thus making it possible to train models with hundreds of trillions of parameters on a few hundred DGX2 nodes. In particular, ZeRO-Infinity fits a trillion parameter model on a single DGX2 node and is able to scale the model size linearly with the node count. In comparison, state-of-the-art techniques like 3D parallelism cannot achieve such massive scales. Next, ZeRO-Infinity provides excellent training efficiency for the largest model sizes, roughly about 500 billion parameters that are trainable by existing state-of-the-art techniques like 3D parallelism. ZeRO-Infinity achieves good training efficiency for models that are larger than this, up until about 20 trillion parameters, where efficiency drops in a noticeable fashion. We've observed that this is due to the small batch sizes and that techniques such as offloading activation checkpoints to NVMe could help here. Next, we observed that ZeRO-Infinity achieves superlinear scaling when training a trillion parameter model on 4 nodes to 32 nodes. This is a weak scaling result where the batch size per node is kept constant as we scale up the node count. ZeRO-Infinity exceeds linear scaling by exploiting the increasing PCIe and NVMe bandwidth. ZeRO-Infinity democratizes model training by significantly reducing the hardware requirements for large models. With ZeRO-Infinity, model scientists can now train or fine-tune models with up to 1 trillion parameters in a single DGX2 node. This represents 2 orders of magnitude increase in model size compared to other approaches. To round up the evaluation section, we briefly examine the impact of two ZeRO-Infinity features on performance. The figure on the left-hand side shows the impact of prefetching and overlapping on performance for different batch sizes. Here we see that for small batch sizes, this feature is very useful because it helps to hide the communication latencies. Whereas for larger batch sizes, this feature is not very useful, and this is because these batch sizes have sufficient computation to hide or amortize the cost of communication. The figure on the right-hand side shows the impact of offloading activation checkpoints to CPU memory for different hidden dimension sizes. For the dimension sizes that would require this feature, which are the extremely large hidden dimensions like 64K, we see here that the overheads of this technique is actually negligible. Now, we revisit our original 3 questions regarding how ZeRO-Infinity could affect the landscape for large model training. We see that ZeRO-Infinity has a positive impact on all 3 questions. First, ZeRO-Infinity makes it possible to scale model sizes beyond the limitations of the GPU memory, thus making it possible to train models that are 50 times larger today. As an example, a 32 trillion parameter model can now be trained on 512 GPUs instead of 25,000 GPUs. Second, ZeRO-Infinity provides broader access to large model training. For example, a GPT-3 size model with 175 billion parameters can now be fine-tuned on a single node rather than 16 nodes. Third, ZeRO-Infinity is easy to use because it does not require model refactoring. And so to recap the performance of ZeRO-Infinity, we see that ZeRO-Infinity enables massive model scale, provides broader access to large model training, provides excellent efficiency for large model training, and superlinear scaling for large model training. This brings us to the end of this talk. To learn more about DeepSpeed, please visit our website www.deepspeed.ai. Thank you so much for your attention.
Okay, I believe we have both Samyam and Olatunji online to answer questions. So if you have questions, please ask them through Slido. Okay, and let's start with the first question, or actually there are a couple of questions along these lines. So there's some question about whether tensor slicing scales beyond a single node, and that there are some other papers that have in fact done this. So I'm wondering about your views on why do you not do tensor slicing across multiple nodes?
Hello. Can you hear me?
Yeah, we can hear you.
Okay, great. So tensor slicing for NLP-based language models, when we mention tensor slicing here, we're specifically talking about transformer-based models, and the most efficient tensor slicing implementation that we're aware of for NLP transformer-based models are the ones that come from Megatron. Those don't scale across multiple nodes. In fact, they don't even scale within a node if you don't have something like NVLink or NVSwitch, which provides really high bandwidth. There might be other operations that could scale, but at least for the transformers, we know that they don't scale beyond a single node.
Okay, so the next question. So I guess I'm going to turn this into a bit of a broader question from Sliders. So it starts with do you expect further improvements by, for example, using NVMMs? And I sort of expand this question to where do you go to next for the models that are even larger than the ones that ZeRO-Infinity supports on current clusters? Do you just have to buy more disks, or is there future work to save more memory and train even bigger models?
Thanks for that question. I think in my view, at least, we're enabling a scale that is so far from what's achievable right now from a compute alone perspective. The amount of compute available on the supercomputing clusters right now, they 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 cannot reach the kind of scales that we are enabling with ZeRO-Infinity. For example, the largest existing language model that has ever been trained, a dense language model, is the Megatron Turing 530 billion parameter model. It took us several months on over 2,000 NVIDIA A100 GPUs to train that model. On the same hardware, ZeRO-Infinity enables a scale that's 50 times larger. So going beyond that is a problem for that we won't have to encounter for several years to come.
Okay, so a question from me. You focused ZeRO-Infinity on optimizations primarily for language models. But nowadays we're using transformers for everything else, image classification with vision transformers and so on. How hard is it to apply the zero optimizations to other transformer architectures that might be using different modalities?
So I think part of the motivation for ZeRO-Infinity is the ability to give data scientists the ability to scale to really large models. And we have not seen the need to scale like multi-trillion parameter or hundreds of billions of parameter model in spaces other than the language model. So for example, even if transformers are applied in the vision space, the size of the models there are much smaller. And so the domain in which we're trying to apply ZeRO-Infinity, it's specifically natural language processing models because of the problem that there the model size is quite large. You could apply it to any other domain where if the model size does become an issue, but we haven't seen the model size becoming a big issue in other domains.
Oh, I'm not seeing any other questions, so I'm going to wrap this up with one final question. So the previous talk in this session was on Megatron and some additional extensions to Megatron for training big language models. So do you think that you can combine these techniques with what you've done in ZeRO-Infinity? I know some of the earlier Megatron techniques you actually do use. And can you combine this, or are there going to be perhaps bottlenecks from the additional model or pipeline parallelism that they're doing impacting the network or other interconnect links?
I think the previous work it combines tensor slicing with pipeline parallelism and data parallelism, and that is a technique that that we have explored in the past, and it, like the deep speed library that ZeRO-Infinity is implemented in, it does support 3D parallelism as well. And it is possible to combine ZeRO-Infinity with 3D parallelism. But I do want to kind of point out that we are targeting very different space. 3D parallelism becomes important when the amount of network bandwidth is really low, and that's where it shines. This can happen when the target batch size that you want to train with is small compared to the number of GPUs that you have, and this would especially happen at scale when you're running on thousands of GPUs. So that's kind of the space that 3D parallelism is really good at. But one of the downsides of using 3D parallelism is it requires intensive changes to the model. So the data scientists would have to go in and change their model architecture to implement all these different forms of parallelism. Whereas ZeRO-Infinity, the way it's implemented, you don't have to make any model changes. So for a large majority of the data scientists who are not trying to train the next 2 trillion parameter model on 10,000 GPUs, that's the space where ZeRO-Infinity can really help without a lot of effort required to scale up. But if it is needed to scale beyond what 3D parallelism can do, it is possible to integrate ZeRO-Infinity with 3D parallelism as well.
Okay, so thank you, and I think that is all of our questions. So once again, thank you, Samyan and Olatunji, for the presentation and being here to answer questions. And we'll move on to the next talk.